Have you ever wondered if there is something out there, traveling from the darkest reaches of the universe, crossing distances that our minds can barely imagine, only to pass before us for a brief instant? Tonight, as shooting stars cross the Mexican sky, a silent visitor watches us from the depths of the cosmos. Stay until the end, because what you are about to hear could change the way you look at the night sky forever.
Good evening, dear audience. I am Felipe Suarez, and allow me to ask you a direct question. Did you know that at this very moment, as you listen to my voice, an object that never belonged to our solar system is crossing our cosmic neighborhood? This is not science fiction, my friends. It is the most fascinating reality that astronomy has given us in recent years. And do you know what is most incredible? That we can see it right now, from telescopes in Puerto Rico and even from backyards in Virginia.
The story begins on an ordinary night, when the automated telescopes of the Atlas program sweep the sky in search of potentially hazardous asteroids. This system, originally designed to protect us from cosmic impacts, functions as a silent sentinel that never sleeps. Every night, its cameras capture millions of points of light, methodically comparing them with stellar catalogs to detect anything that moves in an unusual way. It was during one of these nightly routines when something extraordinary appeared in the data. A point of light that did not match any known object. Its trajectory was different, its speed puzzling. The astronomers who reviewed the first observations felt that particular chill that only those who are about to discover something truly new experience. The object was officially designated as 3I/Atlas. That small letter, I, preceded by the number 3, means something profound in the language of astronomy. The I stands for interstellar, and the number 3 tells us that this is only the third confirmed interstellar object in all of human history. Before it, we only knew Oumuamua, discovered in 2017, and comet Borisov, detected in 2019. Now 3I/Atlas joins this exclusive group of cosmic travelers. But what does it really mean for an object to be interstellar? To understand it, we must imagine the scales of the universe in a different way. Our solar system, with all its planets, moons, asteroids, and comets, is like a small island floating in an infinite ocean of darkness. This island has borders, defined by the gravitational influence of the sun. Beyond those borders begins interstellar space, the void between the stars. An interstellar object is, then, something that comes from that void, something that was born around another star, perhaps billions of years ago, and was expelled from its home by colossal gravitational forces. Since then, it has been traveling alone through the cosmos, crossing distances that defy human imagination. And now, by pure cosmic chance, its path has crossed with ours. The first images of 3I/Atlas revealed something immediately interesting. Unlike Oumuamua, which appeared to be a rocky, elongated object with no visible activity, this new visitor shows typical characteristics of a comet. It has a bright, compact nucleus surrounded by a coma, that diffuse cloud of gas and dust that forms when the ices of the nucleus sublimate as they approach the heat of a star. This cometary activity is crucial because it allows us to study the chemical composition of an object that formed in another stellar system. Each molecule of gas escaping from 3I/Atlas carries with it information about the conditions that existed in its place of origin. It is like receiving a chemical letter from another part of the galaxy, a letter that has traveled for eons to reach us. The telescopes of Puerto Rico have been following this visitor with special dedication. The privileged location of the island in the Caribbean offers exceptional conditions for astronomical observation. Dark skies, stable atmosphere, and a latitude that allows viewing both the northern hemisphere and a good part of the southern celestial hemisphere. From there, astronomers have captured some of the most detailed images of 3I/Atlas to date. In the most recent photographs, taken during the nights of December, the object appears perfectly centered in the telescope's field of view. The background stars, normally fixed and bright points, have become faint lines due to the telescope's tracking. This technique, known as differential sidereal tracking, allows the instrument to follow the comet's movement while the stars appear to slowly slide in the background. The nucleus of 3I Atlas remains compact and bright. There are no signs of fragmentation, no uncontrolled diffusion of material. Only a tight central glow that speaks of a solid, coherent object that is withstanding the stresses of the journey and solar heating. This structural stability is excellent news for scientists because it means they will have more time to study it before it moves away again into the depths of space. The orientation markers in the images reveal something important. The structure of the comet remains aligned even as the stellar background shifts. This confirms that the observed movement is real, not an artifact of data processing, nor an error in the tracking system. 3I Atlas is truly moving through our solar system, following a hyperbolic trajectory that will eventually take it back to interstellar space.
Friends, let me pause here for a moment. Have you stopped to think about what this means for our understanding of the universe? For centuries, we looked at the stars wondering if there was something between them. Now we have the answer, and not only that, we can photograph it, analyze it, study it. Don't you find it extraordinary that we are alive precisely at the moment when technology allows us to see these cosmic messengers? Sometimes I think the universe has a perfect sense of timing.
When astronomers process the images of 3I Atlas using different stretching and intensity mapping techniques, the object reveals additional secrets. A different stretch of the same data exposes the brightness distribution more dramatically, and what jumps out is revealing. The nucleus is extremely compact, almost point-like, surrounded by a smooth and symmetrical brightness drop-off. There are no irregular edges, no chaotic scattering of material, only a tight energy center that maintains its shape with almost geometric precision. The color scale used in these representations tells a clear story. The bright peak at the center diminishes uniformly in all directions. This pattern is exactly what scientists would expect to see if the light source is stable, if the nucleus is not fragmenting or producing random bursts of material. It is a reassuring signal that indicates 3I Atlas is behaving predictably, which greatly facilitates its continued study. Even with the background star trails crossing the field of view, the comet's signal remains clean, fixed, consistent. This confirms what the first observations already suggested. The structure of 3I Atlas is not changing chaotically. Only our way of observing and processing it reveals different aspects of the same underlying physical reality. A third representation of the data completely inverts the contrast. The same object, captured at the same moment, but now the nucleus appears in absorption rather than emission. And this matters because it allows us to see how defined that center really is. The brightness drop-off is rapid and pronounced. There is no diffuse haze extending outward. There are no messy or irregular edges. This type of brightness profile indicates that light is not being scattered randomly by an extensive cloud of dust. Instead, it is being controlled by a very compact region at the center of the object. The nucleus of 3I Atlas, the solid fragment of ice and rock that traveled from another stellar system, is maintaining its structural integrity admirably. The background star trails remain present in this representation, confirming that the exposure conditions have not changed between the different versions of the image. Only the processing is different, and when these three different views are aligned, the conclusion is hard to avoid. 3I Atlas is not evolving chaotically. It is maintaining its structure consistently across multiple methods of analysis. But it is in the fourth processed image where things get truly interesting. Astronomers applied a technique called rotational gradient enhancement. This method is designed to remove the smooth, uniform glow of the coma, exposing any directional structure that might be hidden beneath. And when this is done, something immediately emerges from the analysis. There is a feature pointing forward. It is not a random blob. It is not electronic noise. It is a localized extension emerging from the nucleus in a specific direction. It is subtle, certainly, but it is coherent. It points in a consistent direction and survives even the most aggressive processing. This resistance to processing is the definitive proof that we are not looking at an image artifact. It is a real structural component, physically linked to the central nucleus of the comet. When an object keeps revealing the same geometry, no matter how you process it, that generally means you are seeing the true physics underlying the phenomenon.
Can you believe this, friends? We are talking about an object that comes from another star, from another solar system completely different from ours, and we can see details of its structure. We can see how the material organizes around its nucleus. Doesn't it give you chills to think about this? It does for me. Every time I look at these images, I wonder what stories this traveler carries with it. How many stars has it seen on its journey? How many solar systems has it crossed?
The comparison between observations separated by several days revealed something even more fascinating. Astronomers placed side by side the rotational gradient processed images from December 9th and December 13th. Same observer, same filter, same processing technique. And yet, the structure had changed. The forward-pointing feature in the December 13th images was tighter, brighter, and more concentrated than on December 9th. The nucleus appeared more active, but not more diffuse. Instead of dispersing, it was defining itself more clearly. This is the key point of these observations. Over just a few days, 3I Atlas was not fading into the background noise. It was organizing itself. Its geometry was becoming clearer, not messier. When independent photographs taken nights apart evolve in the same direction, that is not random variation. It is real physical change in the source. This evolution makes sense from the point of view of cometary physics. As 3I Atlas approaches closer to the Sun, it receives more thermal energy. The ices on its surface begin to sublimate more vigorously, releasing jets of gas and dust that can create directional structures in the coma. The fact that these structures are becoming more defined suggests that the comet's activity is increasing in a controlled manner. But the science of 3I Atlas is not limited to large professional observatories. From Virginia, in the United States, an amateur astronomer named Jeff Goldstein pointed his C-Star S50 telescope at the coordinates of the interstellar visitor. With multiple short exposures taken minutes apart, he managed to capture something extraordinary. In his images, 3I Atlas appears clearly, moving against the background of stars near galaxy NGC 3535. The movement is evident and unmistakable. This is not statistical noise, nor a processing artifact. The object is real. It is moving rapidly, and it remains active. These observations from amateur equipment are tremendously valuable to the scientific community. They demonstrate that 3I Atlas is bright enough to be captured with moderate-sized instruments, which enormously expands the network of observers who can contribute data. Each new image, each new position measurement, helps refine our understanding of the object's trajectory and behavior. The trajectory of 3I Atlas is hyperbolic, which means it will never be trapped by the Sun's gravity. Unlike periodic comets like Halley, which return again and again to our inner solar system, this visitor is making a one-time visit. After reaching its closest point to the Sun, it will continue moving away, gradually accelerating toward interstellar space, never to return. This transient nature makes every observation precious. Astronomers around the world are working against the clock to gather as much data as possible before 3I Atlas fades into the darkness between the stars. Every spectrum taken, every image captured, every brightness measurement recorded contributes to our understanding of this cosmic ambassador.
Dear listeners, I want you to stop for a moment and think about this. How many people in the history of humanity have had the opportunity to see an object from another solar system? Before 2017, the answer was zero, absolutely no one. And now, in a matter of just a few years, we have detected 3. Don't you think we are living in a golden age of astronomy? What do you think we will discover in the next 10 years?
While 3i Atlas continues its silent journey through our solar system, the night sky offers another spectacle that is much closer to home. The Geminid meteor shower has reached its peak of activity, turning the nights of December into a festival of fleeting lights. The images captured during the Geminid peak show an extraordinarily active sky. What appears in these photographs is not a single moment frozen in time. It is a temporal composite, a superposition of approximately 1 hour of observation in a single image. The meteors, those bright lines crossing the field of view, tell the story of a cosmic encounter that repeats every year. The Geminids are different from most other meteor showers. While events like the Perseids or the Leonids are caused by Earth's passage through debris left by comets, the Geminids have a more unusual origin. Their parent body is an object called 3200 Phaethon, technically classified as an asteroid, although some scientists believe it could be an extinct comet or a type of hybrid object. Phaethon orbits the Sun in a very eccentric trajectory that brings it closer to our star than any other known asteroid. At its closest point, it approaches only 0.14 astronomical units from the Sun, close enough for its surface to heat to temperatures of over 700 degrees Celsius. This extreme heating can cause thermal fractures that release rock fragments, creating the stream of debris that Earth crosses every December. When one of these fragments enters our atmosphere, it travels at speeds of approximately 35 kilometers per second. At this speed, the air in front of the fragment does not have time to move aside. It compresses violently, heating to temperatures of thousands of degrees. It is this superheated air, not the fragment itself, that produces the bright trail of light we see from the ground. Most Geminid meteors are caused by particles the size of grains of sand. Some are as small as dust grains, and yet they produce flashes bright enough to be seen with the naked eye from hundreds of kilometers away. It is a humbling reminder of the energy contained in motion at cosmic speeds. The radiant of the Geminids, the point in the sky from which the meteors appear to originate, is located in the constellation Gemini, near the star Castor. But this is a perspective illusion. In reality, the meteors do not come from that direction. Simply because Earth moves through a stream of debris traveling in a specific direction, all meteors appear to diverge from a common point in the sky. It is similar to driving a car through a snowstorm. Although the snowflakes fall vertically, from the driver's perspective they appear to converge toward a point on the windshield. The meteor radiant works in the same way, but on a cosmic scale.
My friends, have any of you gone out tonight to see the Geminids? I hope so, because this is one of the best shows the sky gives us every year, and the best part is that you don't need any special equipment, just your eyes, a dark place, and a little patience. Do you remember the first time you saw a shooting star? I do. I was 11 years old and I was in my grandmother's backyard in Oaxaca.
Long exposure photographs of the Geminids reveal something the human eye cannot perceive directly. The meteor trails have subtle colors, which vary depending on the chemical composition of the fragment being vaporized. Greenish tones indicate the presence of magnesium. Yellows and oranges suggest sodium. Intense blues may signal ionized iron. These colors are like chemical fingerprints, revealing the composition of fragments that formed billions of years ago, when the solar system was young and chaotic. Each meteor we see is, in a sense, a message from the distant past, a time capsule that is consumed in a bright flash while delivering its payload of information to our atmosphere. In the composite images of the Geminid peak, the meteor trails intermingle with other bright lines crossing the sky. Some of these additional lines are artificial satellites, reflecting sunlight as they orbit Earth. The proliferation of satellite constellations in recent years has dramatically increased the number of these lines in astronomical photographs. This mix of natural and artificial in our night sky is a symbol of our era. On one hand, we continue to witness cosmic phenomena that have occurred for billions of years. On the other hand, we have filled near-Earth space with thousands of objects that reflect light and complicate astronomical observations. Observing conditions during the Gemini peak were challenging in many parts of the world. Clouds covered wide regions, frustrating the plans of thousands of amateur observers who had looked forward to this special night. But where the skies remained clear, the spectacle was memorable. Observers in rural regions of Mexico, far from the lights of major cities, reported sightings of up to 120 meteors per hour during periods of maximum activity. Some of these meteors were extraordinarily bright, rivaling the brightness of Venus, and leaving persistent trails that lasted several seconds after the main flash had extinguished. These persistent trails, technically known as meteor trains, are caused by ionized atoms in the upper atmosphere that take time to recombine and return to their normal state. During those seconds of persistence, the trail can change shape, distorted by the winds of the upper atmosphere, creating ghostly forms that wind through the sky. The coincidence of having 3I Atlas visible in the sky during the Geminid peak creates an interesting juxtaposition of phenomena. On one hand, we have meteors that are fragments of our own solar system, debris left by an asteroid that orbits our sun. On the other hand, we have a comet that comes from an entirely different stellar system, a visitor from worlds we cannot even imagine. Both phenomena remind us that space is not empty. It is full of objects of all sizes, from microscopic dust grains to kilometer-wide blocks of ice, all moving in complex trajectories dictated by gravity. Our planet travels through this environment continuously, encountering these cosmic travelers in ways both predictable and surprising.
Do you know what fascinates me about all this? That we are connected to the cosmos in ways we are only beginning to understand. Every atom in our body was forged inside a star. The iron in our blood, the calcium in our bones, the oxygen we breathe, it all came from space. And when we see a meteor cross the sky, we are seeing that same process of cosmic exchange in action. Doesn't that seem poetic to you?
The observation of 3I Atlas from Puerto Rico continues to provide valuable data about the nature of this interstellar object. Astronomers are particularly interested in measuring its light curve, the variation in the object's brightness over time. These variations can reveal information about the rotation of the nucleus, the distribution of active material on its surface, and the general geometry of the object. Initial analyses suggest that 3I Atlas has a relatively long rotation period, which is consistent with its apparent structural stability. Objects that rotate very quickly experience centrifugal forces that can contribute to their fragmentation. The fact that 3I Atlas appears to rotate slowly is a good sign for its continued survival during its passage through the inner solar system. Spectroscopy of the object is revealing its chemical composition in ever greater detail. Astronomers have detected the spectral signatures of several compounds common in comets, including water, carbon monoxide, and carbon dioxide. But they are also searching for any chemical anomaly that might indicate an origin in a stellar environment different from ours. Differences in the isotopic ratios of certain elements could be particularly revealing. Isotopes are variants of the same element that differ in the number of neutrons in their nucleus. The ratios of these isotopes are determined by the nuclear processes that occurred in the progenitor star and in the events that formed the planetary system. If 3I Atlas shows isotopic ratios different from those of our solar system, it would be direct confirmation of its extrasolar origin. The path of 3I Atlas through the inner solar system can be reconstructed with great precision, thanks to multiple observations from different points on the planet. Astronomers have calculated that the object comes from a general direction near the constellation Columba, in the southern celestial hemisphere. But this is only the apparent direction of approach. The true origin of the object is lost in the depths of time and space. If we could trace the trajectory of 3I Atlas backward for millions of years, it would eventually point towards some region of the galaxy where it presumably formed. But due to gravitational perturbations from other stars during its long journey, and due to uncertainties in our understanding of galactic structure, identifying the specific stellar system of origin is practically impossible. What we can state with confidence is that 3I Atlas has been traveling for an extraordinarily long time. The distances between stars are so vast that even traveling at speeds of tens of kilometers per second, crossing interstellar space, requires millions of years. This object has been a cosmic wanderer for a significant fraction of the age of the universe.
Think about this for a moment, dear listeners. While dinosaurs walked the earth, while the first mammals evolved, while humanity took its first steps in Africa, this object was already traveling toward us, millions of years of cosmic solitude crossing the void between the stars. And now, for a brief instant, it is here, visible in our skies. Doesn't it seem almost like a miracle of temporal coincidence?
The detection of 3I Atlas is also a testament to the extraordinary advancement of our sky surveillance technology. The Atlas system, which stands for Asteroid Terrestrial Impact Last Alert System, was designed primarily to detect asteroids that could pose a danger to Earth. It consists of several telescopes located in different parts of the world that repeatedly scan the sky, searching for any object that moves against the background of fixed stars. The sensitivity of these telescopes has improved dramatically in recent years. They can now detect much fainter and much smaller objects than before. This technological improvement is the main reason we are discovering more interstellar objects. It is not that these visitors are more frequent now. They have always been passing through. Simply, we finally have the ability to see them now. Statistical models suggest that objects like 3I Atlas pass through our solar system with some regularity. Estimates vary, but some calculations indicate that there could be one or two interstellar objects the size of 3I Atlas within Neptune's orbit at any given time. The challenge is detecting them before they move beyond our observational reach. With increasingly powerful telescopes coming into operation, such as the Vera Rubin Observatory in Chile, we expect the rate of interstellar object discoveries to increase significantly in the coming years. Each new discovery will provide us with another window into conditions in other stellar systems, expanding our understanding of how planetary systems form and evolve throughout the galaxy. The scientific importance of 3I Atlas extends beyond simple astronomical curiosity. Understanding the composition and structure of interstellar objects has implications for our understanding of the origin of life. There is a scientific hypothesis called panspermia, which suggests that the basic building blocks of life, or even simple organisms, could travel between stellar systems aboard comets and asteroids. If this hypothesis has any merit, then objects like 3I Atlas could be potential vectors for interstellar biological transfer. Probably the conditions in interstellar space are too hostile for complex life forms to survive the journey. But simple organic molecules, the precursors of biochemistry, could potentially withstand the conditions of the voyage. Of course, this is highly theoretical speculation. There is no evidence that 3I Atlas contains any type of biological material. But the very possibility reminds us that space exploration is not just about physics and chemistry. It also touches on the deepest questions about our place in the cosmos and about whether we are alone in the universe.
Allow me to ask you something, my friends. Do you believe there is life in other parts of the universe? I personally believe it would be tremendously arrogant to think we are the only ones in this cosmic immensity. And objects like 3I Atlas give me hope. They are proof that material travels between the stars. Who knows what secrets the next interstellar visitor will bring? What mysteries will it reveal?
Observations of 3I Atlas will continue over the coming months, as long as the object remains bright enough to be detected by our instruments. Astronomers are coordinating a global observation campaign, using telescopes on all continents to maximize temporal and spectral coverage. One of the key questions scientists hope to answer is whether 3I Atlas will experience any sudden increase in activity as it approaches closer to the Sun. Some comets show unpredictable behavior, with sudden outbursts that can dramatically increase their brightness in a matter of hours. Others maintain more constant and predictable activity. So far, 3I Atlas has been a relatively well-behaved object. Its brightness has changed gradually and consistently, with predictions based on its distance from the Sun. But comets can be notoriously capricious. A pocket of gas trapped beneath the surface, suddenly released, could cause a burst of activity that would temporarily transform the object's appearance. Astronomers are also carefully monitoring for any signs of fragmentation. The history of cometary astronomy is full of examples of comets that broke into multiple pieces due to thermal and gravitational stresses of their passage through the inner solar system. If 3I Atlas were to begin fragmenting, it would be an extraordinary scientific opportunity to study the internal structure of an interstellar object. But for now, the visitor seems to be maintaining its integrity. The most recent images confirm that the nucleus remains compact and well-defined. The directional feature pointing forward suggests that activity is controlled by one or more specific active regions on the surface of the nucleus, not by uniform sublimation in all directions. This asymmetry in activity can have interesting effects on the object's trajectory. The gas escaping from the nucleus acts like a small rocket, exerting a thrust force on the comet. If this thrust is not balanced, it can gradually alter the object's orbit. Astronomers are carefully measuring the position of 3I Atlas to detect any deviation from the purely gravitational trajectory. These non-gravitational forces, as they are technically known, were particularly prominent in the first interstellar object, Oumuamua. The anomalous acceleration of Oumuamua remains a subject of scientific debate to this day, with some explanations invoking the sublimation of hydrogen ice and others proposing more exotic mechanisms. Observations of 3I Atlas could help resolve some of these controversies.
Before we say goodbye, I want to leave you with one last reflection. Tonight, while you sleep, 3I Atlas will continue its silent path through our solar system. The Geminids will keep falling, grains of cosmic dust burning in our atmosphere, and tomorrow the sun will rise again and life will go on. But something will have changed. Perhaps you will look at the sky differently. Perhaps you will wonder what other secrets the night holds.
The phenomenon of the Geminids and the simultaneous presence of 3I Atlas in our skies reminds us of the dynamic nature of the space environment that surrounds us. We tend to think of space as an empty and static place, but nothing could be further from the truth. It is a place of constant motion, of collisions and encounters, of objects that form and are destroyed on timescales, ranging from fractions of a second to billions of years. Earth, our small blue rock, navigates through this environment like a ship crossing an ocean populated by invisible currents. Meteor showers are the predictable encounters with these currents, the moments when our path crosses the debris left by comets and asteroids that passed through here long ago. 3I Atlas represents something different, a truly random encounter with a wanderer that had never before visited our cosmic neighborhood. The question of how frequently these interstellar encounters occur has profound implications. If objects like 3I Atlas are relatively common, then the exchange of material between stellar systems is more frequent than we thought. This has consequences for our understanding of how chemical elements are distributed throughout the galaxy and potentially for how life might spread. Current models suggest that every star, during its formation process, ejects a significant amount of material into interstellar space. Comets that were part of the original protoplanetary disk are hurled into the void by gravitational perturbations from forming planets. This process has been occurring for billions of years around every star in the galaxy. If we add up all these ejected objects throughout all of galactic history, the result is an enormous population of interstellar wanderers. Some calculations suggest there could be more than 10,000 trillion comet-sized objects floating between the stars of our galaxy. 3I Atlas is just one of them, one that had the cosmic coincidence of passing close enough to us to be detected. This perspective is dizzying when one stops to contemplate it. Every point of light in the night sky represents a stellar system that has probably expelled billions of objects similar to 3I Atlas. And all those objects are out there, moving in the darkness, transporting fragments of their systems of origin across the inconceivable distances of interstellar space. The final destiny of 3I Atlas is to move away from our solar system and continue its endless journey. After passing its closest point to the Sun, our star's gravity will curve it slightly, but will not capture it. It will follow a hyperbolic trajectory that will take it back to interstellar space, where it will continue wandering for millions or billions of years more. It is possible that long from now, when the Sun has expanded to become a red giant and then contracted to become a white dwarf, when Earth no longer exists in its current form, 3I Atlas will still be traveling. Perhaps it will pass near another star, where beings we cannot even imagine will detect it and wonder where it came from. Or perhaps it will never again pass near any star. Perhaps it will wander forever through the void, gradually cooling until it reaches the temperature of interstellar space, just a few degrees above absolute zero. In that ultimate coldness, all activity will cease. There will be no sublimation of ices, no coma or tail, only a silent fragment of a world that no longer exists, traveling forever through the cosmic night.
Friends, we have reached the end of our journey tonight, but before I go, I want to ask you one last question. When you look at the night sky, what do you feel? Smallness before the immensity? Curiosity about the unknown? Connection with something greater than yourselves? I would love to know what part of everything we have discussed today made you remember something from your own life. Let me know in the comments.